So topics for today, we're going to keep going on to conservation of energy. We will get onto momentum and start practicing that when we come back from spring break. But I wanted to make sure we definitely put the time into conservation of energy before we moved on, as it's definitely an important topic. And I think it's one we're all still learning and practicing. So that's going to be the plan for today. We'll go over a few practice problems and go over kind of the general steps for conservation of energy, as it's going to be the same for all of the problems. And if you can get those steps down, then the problems will go a lot better. So kind of go through this. So we're going to start with here is we have a box of mass M, which is being held at h meters above the ground. And a spring with a natural length of L, so that's the unstretched, uncompressed length of L, is located directly below it. So the box is going to go down onto the spring, it's going to bounce, and then it's going to go back up. So we're going to ask and answer a couple questions here. The first one being, what is the speed at the moment it reaches the spring? The second one, what is the maximum distance that the spring is going to compress? And the last one being, what maximum height does the box reach after bouncing back up? So these are all going to be important questions, and we're going to use conservation of energy to solve them. We're given the values of mass, which is 5 kilograms, height 8 meters, spring constant K is 1,000 Newton meters, and the length of the spring, uncompressed, unstretched, is 1 meter. So we're going to start here with identifying the energy, because again, we can't really solve for anything to do with conservation of energy unless we can clearly identify what is actually happening in the system. And so that's where we're going to start. And there's 4 kind of points of interest here. We have the initial point where it's at height h. We have the secondary point where it reaches the spring. Then we have when the spring is kind of partially compressed, but not maximum compression. And then we have the maximum compression of the spring. So all of these are going to be key points that we can use to solve for our answers on the other slide. So what I'm going to have you guys do is take a minute, look at this, think about what's happening at each point, and then in the chat, answer what energy you think is present for A, B, C, and D. Point A is our point where the block is at its maximum height, or at its initial height, sorry. So this is where it's starting from rest, which tells us there's no kinetic energy. We don't have to worry about that. We can also see that the block clearly has some height. So we know that there's going to be gravitational potential, so no kinetic, but there is gravitational potential. And it's not touching the spring yet. If it's not touching the spring, there's no elastic potential because there's no compression. So at point A, we have gravitational potential, and you guys got that. So nice job. At point B, at the moment it's touching the spring, it should be moving. It's been dropped down, so kinetic, definitely. Still has some height, so gravitational. But the spring isn't compressed yet. We're talking about the instant that it's touching the spring. It's not compressed, so there is no elastic potential. Okay, so far so good. At point C, we have partial compression. So partial compression is still compression, so we definitely have elastic energy. It still has some height, it's not on the ground, so we have gravitational potential. And it should still be moving because it's not at maximum compression yet. It hasn't stopped, it hasn't changed direction, so we should still have kinetic. So at that point, we have all 3 types of energy. Obviously, the magnitude will not be the same as at other points because the energy is distributed between 3 types of energy, but they are all present. Point D is probably the trickiest because you have to think about this kind of real life experience. What do you actually see when compressing a spring? Compression for sure, so elastic energy. And as we've seen before, it's not moving when it reaches maximum compression, so definitely no kinetic energy. Gravitational though. So when you guys compress a spring, when you completely hold it between your fingers and you press it all the way down, does the spring get compressed to nothing, or is there still some amount of distance between your fingers if you were to hold a spring? There's still some height, right? So depending on what we're calling zero, a height of 0, things like that, maybe we don't consider potential gravitational, but assuming we're measuring from the ground, we will still have some gravitational potential here. And that's just because of the natural width of the spring when it's fully compressed. It can't be compressed to zero. There's still some material. So we've got that. But yeah, really nice job, guys. You've got all of your, you got all of them right. The last one is just a difficult one because it's kind of, you don't really think about that extra part of the spring. So now that we're starting from here, we can take a look at this, considering what energy is present at each point, and compare them to determine the answers to our questions from the last slide. We're going to start with part one. So we want to know the speed when it reaches the spring. So kind of labeling our points, we have point A, we have point B, we have point C, and we have point D from the previous slides. So for part A, which is to determine the speed when it reaches the spring, what should my initial point be? Keep in mind the initial point is the point that we have the most information about. That's what we want to start with. Point A? Yeah, definitely. Whenever we're doing conservation of energy, we're comparing one point to another. So in this case, we're going to compare the energy at A, which is an information we have, to what should be my final point. What's the point that I'm trying to solve for in this question for part A? Point B, yeah, definitely. I'm asked for the speed when it reaches the spring, so my final point has to be the point that I'm solving for. So the energy at A is equal to the energy at B. We've already determined that the energy at A is gravitational potential only. So gravitational potential at A. And at B, we've said that we have height and we have velocity, but we don't have compression. So we have gravitational potential and kinetic. Keep in mind that I am still labeling these with subscripts. That's so that I can compare gravitational potential at A to gravitational potential at B. If I don't label the subscripts, then it's going to get more confusing when I write these out. So breaking it down, we have mass times gravity times the height at A is equal to mass times gravity times the height at B. Mass doesn't change, gravity doesn't change, so I don't need subscripts for those, but I do need subscripts for the height. And we got 1/2 mass times velocity at B squared. So I can cancel out mass to simplify, which leaves me with the rest of my equation. And thinking about it, do I have enough to solve? I have gravity, or I know what gravity is. I have height. I've been given mass, but I don't really need that right now. So that really leaves one unknown, which is the velocity. And considering that's what I'm solving for, that's going to be completely fine. So plugging it in, 9.8 meters per second squared times the height at A, which is given as 8 meters, is equal to 9.8 meters per second squared times the height at B. And can anybody tell me what the height at B is going to be? Yeah, it's going to be 1 meter because the uncompressed length of the spring, which is the distance from the ground to the spring when it's uncompressed, the top of the spring, is going to be 1 meter. So 1.0 meters plus 1/2 times the velocity squared, and that's what we're solving for. So plug this into a calculator and you get the velocity at B is equal to 11.7 meters per second, which in sig figs is going to be about 12 meters per second. So that is the answer for part A. So all we did was choose an initial point, choose a final point, identify the energy present at those points, write down our equation, break it down, plug in the values we were given, and solve. So those are the general steps that we can follow for all conservation of energy problems. So the answer for part A is going to be 12 meters per second. I'm going to clear this so we can work on the next part. For part B, what we're interested in is the maximum distance that the spring compresses. So we've talked about what energy is present at these points. We've determined kind of what the steps are and how to solve. So for part B, I'm going to have you guys work on this individually for a couple of minutes. So take a minute, think about what your initial point is, think about what your final point is, set up your equations, write it out, and when you have an answer, please put it in the. So we're going to use the energy at A is going to be equal to the energy at our point of interest, which in this case is point D. So we already talked about this earlier. We have gravitational potential at A, and we have at part D, we should have elastic potential, but we also have some amount of height because a spring cannot be compressed to 0. So again, it reminded me of my own points, which just use my subscripts. This is my initial conservation of energy equation. Breaking it down, we have mgh at A is equal to 1/2 kx squared at D, and that's our compression equation. And we have mgh at D. So going through this, we might see a problem here. So mass we're given, gravity we know, height initially we know, so that's all fine. K we're given, and x we're solving for, so that's also fine. Mass, gravity. The problem here is that we also don't know the height at D, so I have an equation with 2 unknowns. So what I want to do here is take my information I don't know, which is this height here, this sort of maximum compression height, and rewrite it in terms of what I do know. In this case, I know that the length of the spring when it's uncompressed is length L, and I know it's going to compress by some distance x. So in this case, I can safely say that that height is going to be the uncompressed length L minus the compression. And this is just going to give me my remaining height because I'm taking the length minus the compression is going to give me my remaining height. That way, in this equation, we only have one unknown, which is x, as opposed to 2 unknowns, which is x and h. So this is how it's going to be written. We're going to plug that in. We have mass, which is 5.0 kilograms times 9.8 meters per second squared times the height at A, which is 8.0 meters. Same step as last time, but I'm just going to repeat it for the sake of making sure that everything's correct in this step as well. 1/2 times K, which is 1,000 newtons over meters. X is unknown so far, but we're going to leave that as unknown, which is fine. Plus our mass again, which I couldn't cancel out this time because it wasn't in all of the equations. And times G, which I'll leave like that for space, times 1 meter minus X. Sorry, it gets a little cramped towards the end there, but that is my uncompressed length minus my compression. Now I'm going to rewrite and simplify this, and I'm going to rewrite it in a way that kind of shows this equation as a quadratic equation. If we multiply it all out, we end up with about 500x squared minus 49x minus 343. So I haven't done any particular math here. I haven't really done anything. All I did was multiply it out and rearrange to write it in quadratic form, so it's kind of clear what you need to do in the next step. Now you can use quadratic equation if you want. I honestly just plugged this into a graphing calculator and found the intercepts. I found that slightly faster. But if you do that, you get x is equal to either negative 0.78 or 0.88. Now the reason we know that it's not negative is because the spring is being compressed, which means I'm solving for a positive value. I'm solving for an actual value in our equation. We've already accounted for signs. So my compression value should be positive. So I can assume it's not the negative one, which for sig figs and everything else is going to give me 0.9 meters, which is the answer. So same steps as the last problem, part A, but maybe a little bit more complex because we had to rewrite and rearrange and solve in quadratic form. But that would be our answer for part B, 0.9. Okay, so for part C, We're solving for the maximum height that the box reaches after bouncing off the spring. And the answer for this is actually going to be 8 meters. So can anybody tell me how I can just automatically say that it's going to be the same height as the initial height? How do I know that? What's the reasoning? Yeah, all the energy in this situation is going to be conserved. It's going to be converted back to potential energy. There's no loss of energy. So in this case, assuming no air resistance, all that stuff, there's no non-conservative forces. There's no non-conservative energy. Energy isn't being lost to anything like friction, things like that. So the energy at the beginning has to equal the energy at the end. So kind of, we'll go through the steps here, but keeping that in mind, we can say that this answer should be 8 meters. And if we get something different, that's a sign that something's not right. But again, initial point is going to be point A. And my final point, I'm just going to say max, because we don't really know where that is. We can say logically it's going to be point A, but leaving it for now. At point A, I have mgh. I have, my potential gravitational energy. And at my maximum height, there's no kinetic energy because there's no velocity at the maximum height. There's going to be no compression energy or elastic energy because the spring isn't going to be anywhere near the block. So that only leaves potential gravitational energy. So again, we'll have mgh at max. So the mass is consistent and can be canceled out. Gravity is consistent and can be canceled out. So we can say both logically and through our equations that the height initial is going to equal the maximum height, which is 8.0 meters. If there were other forces like friction, like air resistance working on this, that would not be the case. In real life, that's not the case because energy is usually lost. But for the sake of this problem, our answer should be 8 meters. In this case, we have a block with mass of 0.5 kilograms is forced against a spring with a negligible mass, compressing the spring a distance of 0.2 meters. When released, the block moves on a horizontal tabletop for 1 meter before coming to rest. The force constant K is 100 Newton meters. What is the coefficient of kinetic friction between the block and the tabletop? So we're trying to figure out what mu is equal to. So what are our 2 points of interest in this case? What's my initial point that I want to? Yeah, when the spring is compressed, so this point here, because I've been given all of my distances are measured relative to that point. Like my 1 meter is measured relative to that, and I've been given information. So at that point, when the spring is compressed, what energy is present at that exact point? Elastic potential, yeah. There's no difference in height across this problem. The block is on a flat surface, so we're not worried about gravitational change in gravitational energy. Kinetic will be an issue, but not at the point where it's maximum compression, because that's an initial point. So we can say that, let's call this A. The energy at A is equal to, and we're saying that this is elastic potential at A. What is my secondary point? What's my final point that I'm interested in? This should also be a point that I'm given information about. When the block stops, yeah, definitely. That's the other point. I've been given information about 2 points, the point of compression and the point where it stops. So those kind of have to automatically be my points of interest. So energy at B. And at that point, what energy should I have? So what is the block doing at this point, at block B? The block stops, right? So if it stops, no velocity means no kinetic energy. It doesn't have any height, it's not touching a spring, so it should have no energy. There's no kinetic energy, there's no potential energy. It should have no energy. So how do we explain this? Energy isn't created or destroyed, so where has the energy gone? Friction, right? So we have The elastic potential A is equal to the energy that is lost to friction, or our work non-conservative. So we're going to look at this and break it down. We have 1/2 kx squared, x at A. And this should be equal to our work non-conserved. And what is our equation for work? Work is equal to what? Force times distance. And in this case, we've said that the force is friction. So that should be friction times distance. What's another way that I can write friction? Mu times normal. Yeah, definitely. Mu times normal, again, times distance. And can I break this down further, or is that kind of the end of it? How else can I break this down? On a flat surface, what is the normal force equal to? Mg. Yeah, on a ramp, it's different. On a flat surface, we're equal to mu times mg times distance. So I can say that 1/2 kx squared at A, so my elastic potential at A, is equal to the work that is done by friction, which is mu times mg times d. So taking a look at this, I have K, I have the compression, I have mass, I have gravity, I have distance, and my one unknown is what I'm solving for, which is mu. So this equation is going to be useful to me. I can solve from here. So 1/2 times 100 Newton over meters times 0.2 meters squared is equal to mu times our mass, which is 0.5 kilograms, times 9.80 meters per second squared, times our distance, and our distance that is traveled is 1 meter, which is given in the problem. So plug this into a calculator, and we can get that mu is equal to 0.41, and it should be unitless. And for sig figs, that should be about 0.4. So again, same steps, even though we weren't solving for, we were solving for a coefficient instead of a value. The concept is the same. We're still setting up equations. We're still choosing points of interest. This one, we had non-conservative forces, but apart from that, everything is the same as the last example. Kind of general reminder, there's no sessions over spring break. So the next session will be on that Monday following the break, which is the 5th of April. If you guys have any questions, feel free to email me about anything. Apart from that, have a happy spring break. I hope you guys get some rest and get a chance to give your brains a rest and take some